Hello, and welcome to Empowered Learning. This video will be about how to come up with derivatives using the difference quotient, or as we say, finding derivatives using the definition of a derivative. A derivative, in short, is just a way to be able to express instantaneous rate of change of some function at a particular x value. And so what we end up doing here is, since if you're watching this, then you've probably talked about limits in your courses, or if you're studying calculus on your own. And you've also probably also talked about continuity in that particular concept as well. And so we need both of those to be able to get into the realm of actually being able to express derivatives in the language of calculus, which is basically using limits and the difference quotient. And so what I have here is the definition of how we define a derivative. And so I start off by just interpreting it as the slope of a tangent line, and then we move on to actually calling it a derivative. So we first start off with the definition of the slope of a line tangent to a particular point a f of a for a function. So what we mean by a line being tangent to a point is we have a curve, and that curve just is intersected by a line at exactly one point and nowhere else. So that's all we mean by that. And so this definition says the tangent line to the curve of y equals f of x at the point a f of a is aligned with the slope, and we find the slope by taking the limit of the difference quotient, which is just a fancy way of expressing the slope of a line. And we have all these different ways of expressing it. And so as you see here, in this form, we have it to where, and I'm just going to draw a function here. So let's say I have this point and I have this point. So here, this could be the point a f of a, and this point could be the point x f of x. Of course, if I have a line through there, if I find the slope is going to be the rise over the run. And if I label this my x2, y2, and this my x1 and y1, if I put that into the formula for the slope of a line, you'll see here that I just end up with f of x minus f of a, because that's my y2, that's my y1, divided by x2, which is just x, minus x1, which is just a. So that's what that is. And so if you notice here, what we're actually saying as x approaches a, we're saying that the distance in between x and a are getting closer and closer together. So in this sense, what's happening is I'm taking this point right here, and I'm starting to try to move it closer and closer and closer to this one, okay? I could also go the other way and try to move this point closer and closer to that one. So we could also look at it that way. Either way, what we end up with is there is a line that will go through this particular point right here, and that line would be what we call the tangent line. And the slope of that line would be what we call the slope of the tangent line. And that's one of the ways that we interpret a derivative. So that's what this is about. Now, for this version of the difference quotient, all that we're saying here is that the concept is the same, but the way that we label the points are different. So what I'm going to do is I'll erase what I have here. Well, not all of that. So let me get just this part. I'll erase this. And now, instead of naming this point x f of x, what I'm going to do now is say, we know that this particular point is at an x value a, and if I go a distance of h units over, now I'm at a plus h, and so the corresponding y value would be f of a plus h. And so again, the same type of thinking here, if I were to use the formula for the slope of a line, we would see here that if we plug that information in or evaluated this using that, Then the f of a would be the y2, f of a plus h would be the y sub 2. The f of a would be y1. And of course, the x2 would be a plus h. And the x1 would be minus a. And of course, those a's would cancel, and all I would have left in the denominator is h. And so you see how we end up with that form of the difference quotient. What we are talking about here is what we have been coming up with as far as formulas is really the slope of a secant line. And a secant line is defined as a line that intersects a curve at exactly 2 points like what you see here. And all we're saying is that the behavior of this secant line, as we start to move this point closer and closer to this one, the slopes that are the lines and their corresponding slopes that are produced get closer and closer to the actual tangent line. So I'm going to pause this video for a second and draw the tangent line and then draw another secant line so you can see how the tangent lines actually morph into the secant lines. So we see here, now that I've drawn these lines, the pink or magneta line that you see here is, I've taken this point, a plus h, f of a plus h, and I moved it up some. And so now if I have that, then you see that the slope of the secant line that's made by this point and that point turns from being negative, like how we had it here, to now being positive, okay? But it still is not as positive as it needs to be a tangent line. And so, of course, if we move this point closer and closer and closer to here, to where it's theoretically on top of this point that I'm on right here, then we have the red line. And that red line is what is called a tangent line. And so it's the slope of this tangent line that gives us the instantaneous rate of change at this particular point. Or put another way, how fast this particular function is changing exactly at this particular point there. So that's the idea behind the derivatives. Where the limits come in is we're basically talking about the behavior of the slopes of secant lines. And as we move those points closer and closer to the point we're actually trying to find out the instantaneous rate of change of, the secant line slopes tend to morph into or turn into, or the behavior of them get closer and closer to the actual slope of the tangent line. And thus, it's the derivative. So to get a better idea of this, I want to go back to some previous content I've covered before, just to make sure that this concept sticks. And so I'm going to review some notes again, just so that you kind of get this idea here. You see it actually happen empirically. And then from that, we'll come back here and finish up this particular portion of this video before we start doing example problems. All right, so this comes from material I've had when we talk about basic limits of a function and trying to sort of understand what that concept is. So we know that a secant line is a line that intersects a curve at exactly 2 points. And we know that the informal definition of a tangent line is a line that intersects a curve at exactly 1 point. So I say that this is a crude way of saying this because if we look at the figures below, we'll see that that definition doesn't always hold in regards to what it is that we're actually implying. So figure 1 actually talks about or shows when you've probably first heard of something being tangent to a particular curve, the concept of centripetal force is probably what you heard of in your physical science courses. And so this sort of models you're spinning around something and you want to know the force of some object that's tied to the end of a string at a particular moment. And so, of course, if we found out the slope of this line, that would give us how much force it would be if we're measuring everything in, let's say, newtons. So this is what you probably seen the first time we talked about something being tangent to a curve. Now, figure 2 here is an example of what we actually do mean when we say we want to find a tangent line. So here we have these 2 points, and these 2 points are slopes of a secant line, which is curve, and that curve is being intersected by a line at exactly 2 points. But here at point P, this line is what we call our tangent line. That line intersecting the curve at exactly 1 point. Now, the thing that's implied here is that whenever it intersects it, we see that the slope of the tangent line actually goes along with how the graph is decreasing at that moment. So that means, hey, the slope of the tangent line says that, hey, this function is falling or decreasing at that particular x value. And so that's what we actually mean when we want to say the slope of the tangent line, okay? In this instance, it doesn't follow that. If you notice, my tangent line has a positive slope here, but my secant line has a negative slope. And so it's really the tangent line that's the issue here, because of the fact that we see that at point Q, this particular function is increasing, but it's not increasing to the rate as the line T is. So if I wanted to draw a proper tangent line, it would look like this. So it looks something kind of like this. So we come here, look something to that effect. And so you see the slope of the red line, of course, is lower than the slope of the line T that we have here, because that's almost an infinite slope. So the slope is very, very high. But we see that our function, it is increasing in a positive direction, but it's not increasing to the tune of it being almost an infinite slope. So this is what we mean when we talk about tangent lines. So now what I want to do is let's carry on and look at this particular question, and we're going to figure out what is going to be the equation of the tangent line, which of course we'll need the slope in order to figure that out, of this function y equals x cubed at the point 2, 8. Okay, so in order to find the slope of the line, we need the slope of the line in at least 1 point. Okay, and so to find the slope m of this line, we will first look at the slope of the secant line between some arbitrary point x and x cubed on y equals x cubed at this particular point. Okay, so if we recall, we know that the slope of the secant line is just, of course, the slope of a line. And if we're looking at this in terms of the points being x f of x and x plus h f of x plus h, our difference quotient, or the way that we express the slope of a line arbitrarily, looks like this. Now, since we actually have a defined point that we're referencing everything to, we want to use this form of the difference quotient, because this refers to saying, hey, I want to find the slope of a line in reference to a specific point, a f of a. And of course, our a f of a here is the point 2, 8. Where a is the number 2 and f of a, or f of 2, is 8. And so that's how we end up getting this form of the secant line, because we're just doing f of x minus f of a over x minus a, where your a is 2. So we get this. So now what we want to do is we want to investigate the behavior of the slope of the secant lines as they approach 2, going from the left and the right. Okay, and so one way you can do this, you could put this particular function in your calculator, and if you put it in your calculator and do it for several values of x, like how I have listed here, you will see that these numbers, as we get closer and closer to 2, will start to get closer and closer and closer to some value. All right, so once we put this function into our calculator, we can use the calc feature if you're using a TI-83 or 84 to figure out what these values are. So if we do plug in 3 in for x, we'll see that the result that we get is 19. And then, of course, if we do 2.5, then we get 15.25. We do 2.1, get closer to 2, we'll have 12.61, 2.001. Let's see, we'll have 12.006001. And then if we go to 2.00001, then you see that we will get 12.4 zeros and a 6. 12.4 zeros and a 6. So as you can see, as we're coming from the right of x equals 2, it looks like we're getting closer and closer to 12. If we go the other way, we plug in 1 into our slope of the secant line, which could also be called the difference quotient, we see that we get 7 in that case. If we do 1.5, we get 9.25. If we get 1.9, then we get 11.41. 1.999, we get 11.994001. And then 5 nines after the decimal, and we get 11.99994. So you can see, coming from the other way, it looks like we're getting closer and closer to 12 as well. So what's actually happening here is that as we take these points, and I'm going to go back up to the picture that we had. So as we take these points here and we move them closer and closer, whether we're coming from this direction or this direction, and we move closer and closer to the point 2,8, the slope of the lines that we the slope of the lines that we draw through each of these pairs of points here tends to start to get closer and closer and closer to what the actual slope of the line is for this line T that we see right here. And it looks like it's going to 12. So empirically speaking, we can see that the slope of our tangent line should be going to 12, okay? And so if it looks like that, then of course we could just use that and the point 2,8 to be able to find out what the equation of the tangent line would be. But I wanted to show you this because I wanted to show you what does it mean when we say the behavior of the secant line, or put another way, the limit of the secant line, as in this case, x approaches a is going to be the slope of the tangent line. And of course, our a in this case is 2. So as x gets closer and closer to 2, coming from both the left-hand side of 2 and the right-hand side of 2, we see that the slope of the secant lines tended to get closer to the slope of the tangent line, which is 12. So that's what we mean by that. So again, as x approaches 2 from both the left and the right, the slope of the secant line seems to be approaching 12. And so the tables that we did previously as x approaches 2 from both the left and the right were showing how the slope of the secant lines change from our point, arbitrary point, x cubed, okay? That is to say, the behavior of the slope of the secant line changes as this point changes, okay? The behavior of the slope of the secant line as x approaches 2 from either side acts as if it's approaching that same number of 12. And the behavior of the slope of the secant line as x is limited to approaching 2 is called the slope of the tangent line. And so here I'm just making a point of what we've already mentioned before. And so we look here, we know that when we talk about the slope of a tangent line, it is the same as the behavior of the secant line as x approaches some specific value a. And of course, for this example, we know that that was 12 for the tangent line. So now what we want to do is find out what is going to be the equation of the tangent line with the slope of 12 and the point 28. Of course, here we could use the point slope form of the equation of a line, where 2 will be our x1 and 8 will be our y1. So if we did that and just substituted everything in, we would see that, of course, y minus 8 here, it'll be 12x minus 24. We add 8 to both sides, and we see that our result here is y is equal to 12x minus 16. And that is what the slope, the equation of the tangent line would be there. All right, so now you kind of see why we're talking about this difference quotient here and why we're actually talking about it or looking at it as the formula for the slope of a line. It's just the points that we use could be arbitrary, okay? So now what we do is we extend this idea of the slope of a tangent line to now trying to define what a derivative is in terms of taking the behavior of the slope of a secant line as it gets closer and closer to some point of reference. And so that's what the definition of derivative can be expressed as. So here, derivative of a function at some number x equals a, the definition of it. We say that the derivative of a function f of x at x equals a, where a is some real number, is denoted by this notation here, and we call this prime notation because of the little ticking mark that you see right there. And we look at it this way: the limit of the difference quotient, whether you're going to look at it this way or this way, as the horizontal distance in between the values, the horizontal distance in between the coordinates get closer and closer to 0, okay? So again, in this first form of the difference quotient, our points are a, f of a, and a plus h, f of a plus h, where h is some specific real number. What we're saying here is that as the distance in between a and a plus h dwindles or gets closer to 0, meaning that h is getting closer and closer to 0, then the slope of the secant lines by these 2 points will eventually turn into a tangent line. And of course, here we're saying as x gets closer to a, because now the 2 points are a f of a and x f of x. And we want this to get closer and closer to a, to where the distance in between these 2 points horizontally would be 0. And so that is how we define our derivative. Now, in noting that, note that in order to be able to define and find derivatives this way, we have to know how to evaluate the difference quotient. So a lot of what we're going to do here is actually practicing on different ways to evaluate our difference quotient depending upon what type of functions we have. And so that's the trick to doing this. The actual evaluating the limit part, once we have our difference quotient in a form that's malleable to us to be able to actually evaluate it by plugging in this case, 0 for h or a for x. That part is actually simple. So we just need to have our difference quotient in a form that makes it easy for us to plug it in. And what we mean by that is we don't have 0 in the denominator whenever we're doing that. Because if you look here, if I just plug in 0 directly here, I'm going to have 0 in the denominator. And if I plug in a here for x, I'm going to have 0 in the denominator. And that really doesn't help me out because we already know that's going to happen. So we need to get our difference quotient in another form to really let us know what's going on. All right, so let's look down here where we have the average rate of change versus instantaneous rate of change. And so I have this here because this is another interpretation of how we can look at the derivative or the slope of a tangent line versus the slope of a secant line. In short, when we look at the average rate of change, this is sort of modeled as the slope of a secant line, whereas instantaneous rate of change is looked at as the slope of a tangent line. What you see here is we're going to look at the difference quotient in another way. And so if we let the change in x mean x2 minus x1, and the change in y being y2 minus y1, which could also be expressed as f of x2 minus f of x1, then we could rewrite the slope of a line in this form or this form. And of course, all that is just another way of expressing the slope of a secant line. Okay, so we know that all these forms here, whether we use the delta notation, function notation, or just call it difference quotient, it all means the same thing. And so we can also look at the definition of a derivative, and what we have is called incremental notation. And so for those of you that are going to be studying business calculus, you'll actually see this in an area called incremental changes. And so you'll use that to be able to estimate future prices for things. And so you'll see that later on in your course. For those of you that are taking traditional calculus, you may or may not see that depending on who is teaching it and what needs to be covered. But just know that this is another way of being able to express a difference quotient and thus the limit of that, meaning another way to express a derivative. Now, the main connection that we want to have here is that whenever we see or want to know the instantaneous rate of change of a function, that can be translated as the slope of a tangent line, which can be translated as finding derivative of a function at some specific value x equals a, which could be translated as the slope of a secant line for this particular function at two arbitrary points, as the horizontal distance in between those 2 points gets closer and closer to 0. And that's also known as taking the limit of the difference quotient. So now that we see that the limit of the difference quotient is a way for us to find the slope of the tangent line, we can do that problem that we said before just by doing limits instead of having to do it empirically. Okay, so here let's look at finding out what the derivative of this function would be at 2. And we're going to use this form of the difference quotient to be able to do it. And so to do that, we'll say that this will be the limit as x approaches 2 of f of x minus f of 2 over x minus 2. And so we're doing this because this first part here is going to give me what the slope of the tangent line will be. In order to find the slope of the tangent line, I just know that it's an interpretation of the derivative. Okay. So in doing this, we know that f of 2 is just going to be 8 because we know 2 cubed is 8. And we know that f of x is just x cubed. So if we come here, we see that f of x is just x cubed, f of 2 is 8, and this is just x minus 2. Now, we know that x cubed minus 8 is the difference in between 2 cubes. And of course, we know that 2 cubed is 8, so we can look at it this way. We have special factoring rules that tell us that x cubed minus, in this case, 2 cubed would be x minus 2 times x squared plus 2x plus 4. And so how we get that is we know that x cubed minus a cubed in general is x minus a times x squared plus ax plus a squared. And of course, if our a is equal to 2, then we know that's why 2 goes here, and 2 squared, that's why 4 goes there. So now in knowing that, we could rewrite what we have here in the limit as x minus 2 times x squared plus 2x plus 4, all in the numerator, and in the denominator it is x minus 2. So in looking at it that way, we see that these factors reduce to 1, and so we know that what this means whenever you have common factor in numerator and denominator for a rational function is that you have a hole in your graph. Okay? And so here what we're saying is this rational function is going to act just like this polynomial or quadratic function here as x approaches 2 from both the left and the right. And from here, we know that since this is a polynomial of degree 2, the direct substitution property says that since 2 is in the domain of this polynomial, and that this is a nice, smooth, and continuous function, that we can just go ahead and plug into or evaluate this polynomial at 2. And of course, if we finish up the math there, we see that the result is 12. And that's the exact same thing that we found whenever we did it empirically. And so this is the point that we were trying to make. If we can successfully evaluate the difference quotient, then we can easily figure out what the slope of the tangent line is. And of course, the connection here is that the slope of the tangent line is the same as taking the derivative of this function, specifically at x equals 2, and that will equal 12. Okay. So now that you sort of got the concept of what a tangent line is and how that's related to a derivative and what the concept of a derivative is, I hope you check out the next part or the next version of this video where we get deeper into some other examples and some other techniques to be able to evaluate difference quotients.